Since matter is a gigantic concept that encompasses much of the world around us, chemists divide up that concept into different types of groups. There are many different ways that this is done in practice. For example, you could divide matter up as pure substances or mixtures. Some objects are pure substances, meaning there is only one type of matter present in the sample. A couple of different examples of pure substances are given here. There's some copper bars, there's some sugar cubes. In both of those cases, there is only one type of matter present in the sample. The matter might be a molecule in a compound, as is the case in the sugar. We would still say the sugar is a pure substance, because there is only one type of compound present in that sample of sugar. Other types of matter are mixtures of two or more substances. Mixtures can be further classified as either homogeneous or heterogeneous. Let's take a look at the homogeneous mixture. In that particular example, which is a cup of tea where all of the sugar has been dissolved, any sample that you took from the container, in other words, if you took your spoon and scooped out some tea, since there's no tea leaves at the bottom and there's no undissolved sugar, any sample that you took would be uniform throughout the entire sample. In contrast, in the example that's given for the heterogeneous mixture, which here is a mixture of water and oil, you see there is an interface between the two substances that make up the mixture. And if you took your spoon and took a sample from the top layer, you would get a sample of oil. But if you decided instead to take your spoon and take a scoop from the bottom layer, you'd get a sample that's mostly water. So in that case, the mixture is not uniform throughout, and we say that it's heterogeneous. Another way that matter can be classified is by phase, which is also referred to as physical state. You are very familiar with three states of the ubiquitous water molecule, for example. Ice is water in the solid state. Liquid water is the type of water that you can drink. And there's also water vapor in the air around you, and we call that humidity. People also call water vapor steam. If you look at these pictures, you can see representations of each of the types of phases of water. At least three of the types. There's actually a fourth phase called supercritical fluid that we won't be discussing here. An artist has rendered depictions of what the water molecules look like in these different phases of water. In the solid phase, the water molecules are very much highly organized. In fact, they're even more organized than is shown in this picture. And there's different types of ice depending on the organization of the water. But those water molecules in ice are quite tightly packed and well organized. In the liquid water, the water molecules are still close together, but they're not as well organized. Here, in all of these pictures, the oxygen is shown as a red sphere, and the hydrogens are shown as white spheres. Finally, in the gas phase, the molecules are completely disorganized, and they move completely randomly and independently of each other. A lot of times people think that we can see the vapor phase of water, but we can't actually see it. What we see when we see steam coming off of a cup of coffee, for example, is tiny droplets of the water that have gotten large enough that our eye can detect them. When water is really in the vapor phase, the molecules are so far apart from each other that we can't actually see them. So there's some water vapor in the space up here where we can't see anything. Water in the vapor phase is clear and colorless and invisible to us, although sometimes we can tell that there's a lot of water vapor in the air from the way it feels on our skin. Although you can look up the information about the elements on the periodic table, I think that it's quite handy to have some of the information about the common element names and symbols stored in your head for quick and easy recall. So please consider memorizing the following element names and symbols. You don't need to memorize the atomic numbers. I'm just listing those atomic numbers there so that you can see which ones you need to look up. But I do think that you should know that H is hydrogen, C is carbon, and O is oxygen. Go ahead and learn the symbols for the elements that are the lowest 36 atomic numbers. You should also know all of the halogens, fluorine, chlorine, bromine, and iodine at least. At least know those four. The noble gases are also a good group to know. That's the group that has helium and neon at the top. So know all of those, all the way down through radon. Radon is actually common in nature. People do radon testing under their house. Radon is a radioactive gas, and so it can cause cancer. So you should, if you buy a new property, you should always be sure to see if there's radon common in the Earth's crust in the area where your house is. And if there is, you need to be sure that you have the crawl space or basement of where you're living checked for radon. It's known as a health hazard. There's a few other metals that are common and we'll be using regularly in this class: tin, silver, gold, ruthenium, mercury, lead, barium, platinum, palladium, and uranium. So I think you ought to know those symbols as well. I don't want you to get confused when I say lead and you don't realize that it's Pb. Other basic information about matter that you should know includes which elements exist as diatomic molecules in nature. As I mentioned earlier, most types of atoms are unstable by themselves, and therefore they prefer to react to form molecules. Some very common substances in nature usually occur as diatomic molecules. It's a good idea to know that because it can help out with reaction calculations. So for example, if I told you that octane was burned in the presence of oxygen, you would need to know that the oxygen in nature is not just an oxygen atom, it's the molecule O2. The same is true for nitrogen, which is N2, and hydrogen, which is H2. Remember, we saw the explosion of a hydrogen balloon before, and it was actually H2 molecules that were burning in the presence of the oxygen. Halogens also exist in nature as diatomic molecules most commonly. So if I told you you had a reaction of chlorine, for example, the chlorine in the swimming pool, it's probably not a chlorine atom. It's probably a Cl2 molecule. So those exist as F2, Cl2, Br2, and I2. Or some people remember it as their favorite rock band, Hahn and the Halogens. That's a good way to remember the atoms that exist as diatomic molecules. Other basic information that comes along, that you might want to memorize as it comes along, are things like the Greek alphabet symbols as we use them. So if I say C equals lambda nu, and I write that equation, you need to know that when I say the word lambda, I mean this symbol right here. Finally, it's a really good idea to know the common SI units and prefixes. We talked about that earlier when we did the unit on measurements. But you need to know that mega means 10 to the 6th, and kilo means 10 to the 3rd, and nano means 10 to the minus 9, for example. It's also a good idea to know that length is measured in meters, time is measured in seconds, and kilogram is the common units for mass. All of those things are good to know, so I think you should consider learning those. The world around us is dynamic, and matter doesn't always stay the same. In the next video, you'll see demonstrations of both physical state changes and chemical changes that affect the composition of matter. In a physical change, the state or appearance of the matter alters, but the composition of the matter doesn't change. An example of that you've experienced is solid ice melting to make liquid water. That's a physical change. The ice, of course, is physically much different than the liquid water, but the molecules haven't reacted with other molecules to form different types of bonds. In both cases, we have an oxygen with two hydrogens bonded to it. The only difference is in the level of organization of the molecules and how they interact with each other. In a chemical change, the composition of the matter is altered. During the chemical change, the atoms actually change partners. They rearrange to form new molecules, but all of the original atoms are still present, and that is called the law of conservation of matter. So the atoms can react and form bonds with other atoms, but the total number of atoms in the reaction doesn't change. So we've defined atoms, elements, molecules, and compounds in this lecture. Matter can change phase. For example, some types of matter can be a solid, liquid, or a gas. Or matter can be present in mixtures. Matter can also react with other matter, but when it reacts, the atoms merely change partners. Both phase changes and reactions involve changes in energy. So energy will be the topic of a future video. Remember, matter has mass and occupies volume. All matter is made from atoms and molecules. Everything that you eat and drink, all of your clothes and furniture, all of that is composed of matter. That means all of those substances are actually made of chemicals. Whenever you eat food, you're eating chemicals. Matter can change phase and it can react with other matter. In the next video, I'll be showing you chemical demonstrations of phase changes and of matter undergoing reactions. So please tune in and watch that video soon. Thanks.